Today's lecture. Actually, if you recall, we were doing estimation using linear models, and then I thought that we have seen that the first basic equation, which is called the normal equation, involves that equation involves the correlation matrix. If you want to get the optimal weights, you have to get the correlation matrix. So it is a natural question as to how am I going to get the correlation matrix. So that's why we made a kind of a backtracking, and we are today covering one topic just to see how correlation matrix and their Fourier transforms, which are power spectral densities, are to be estimated from a given data. Now, basically the problem that we will be seeing is that stochastic process means that there are many realizations possible depending on the outcome of the experiment. Every time you get one signal. So in general, autocorrelation, power spectral density, everything will mean that you have to take an average of some quantity over ensemble. Everything is an expectation. So expectation means that it is an average over ensembles. Now, but while it is so, that is how it is defined, but it is very difficult to estimate that way. Then we have to get multiple signals. We have to actually carry out the experiment. We have to get multiple signals. Then we have to carry expectation. That is a cumbersome procedure. So in many cases, what we are interested in is that given a single realization of a process, how we can estimate those quantities, and whether those estimates are any good or not, because multiple realizations are generally difficult. Secondly, theoretically speaking, everything is being all DFT, everything is defined from plus infinity to minus infinity and all. All realizations are assumed to be from time minus infinity to plus infinity. Now again, that is a theoretical abstraction. You cannot get that. So you will get a finite length sample sequence in general. So what is the impact of having a finite length sample sequence? Because the quantities that we want to estimate are actually defined over infinite length sequences. So that is the basic thing that we will examine today, that given a single realization of a finite length sequence of a stochastic process, how to estimate its correlation and power spectral density, and what are the ways of improving them and things like that. That is the basic topic. So it's it's the ways of practically realizing the correlation and the power spectral density, which you can actually follow in practice. So we'll just once review the autocorrelation and PSD. These are all well known. That is, the autocorrelation is defined as Rxx Mn for a general process is expectation of Xm into Xn. We are talking about real processes, so there is no complex conjugate involved here. Everything is real. If the process happens to be stationary, that is wide sense stationary, then the correlation depends only on m minus n, right? And obviously you can exchange the arguments. You can m minus n and n minus m are the same. So this is the case. In case if you can define another signal which is obtained by filtering it, convolving it through a filter of impulse response H, that is, if y is the output of a filter whose input is X, then we know that the cross correlation is defined like this. this we have already derived, and the autocorrelation of the output can be defined in terms of this or in terms of this. So these that is you can go on convolving them with the impulse response. In terms of frequency domain, the power spectral density is actually defined like this. So remember one thing, that even if, see, now we are talking of Rxx so our time signal is sampled. The time sequence is discrete, but that doesn't mean that the frequency Sxx is discrete. It is actually a continuous function of omega. Okay, that must be remembered. And similarly, if you want to get Rxx, then you have to get it through the what is known as the inverse Fourier transform, and the frequency domain representations of these two relations are these two relations, that is Rxx convolving with h of minus k is in the frequency domain like multiplication with h star omega. So finally you get Syy omega is Sxx omega into magnitude of h omega square. This relationship we have seen. Okay. So now we come to our actual problem. Our problem is to estimate, first problem is to estimate the autocorrelation from a single realization of a finite data sequence. So we have a data sequence xn, which we have from time 0 for n is equal to 0 to n is equal to capital N minus 1. So we have capital N number of points and only one sequence. Now how do you, and we obviously we assume a stationary process. So because unless you assume stationary process, you cannot write it as Rxl, right? So it's simple, that is, see, we are assuming, what we are assuming, that we are assuming that the ensemble average can be replaced by time average. See, we have only one realization, so therefore there is no question of having an ensemble average. We have only one realization. So if we want to make any average, we can only make a time average, because we have samples at various sequences. So if the ensemble average, we are again assuming that, so if the ensemble average is equal to time average, then we can take a time average. And remember that, see, that these indices have been so carefully formed that actually I mean, ideally speaking, we should form an infinite time average, but we cannot do that, of course, because we don't have samples. So these indices have been written carefully so that none of these will actually fall beyond 0 and n minus 1. See, when maximum value will be n plus l, maximum value of small n is n minus l minus 1. So maximum value of this one will be capital N minus 1. It will not exceed. Okay, and the minimum value is going to be the minimum value here. So for this time instant, this is defined as the autocorrelation for positive L, and the autocorrelation for negative L is actually simply defined. It is as such defined like this. That is, you could have defined it in some other way, like you know, so that is, for example, you could have written a different expression for this here, but then what expression? For example, this is, you could have written that actually if you take Rx minus L, it is going to be x n minus L and xl, right? So x n minus L, now n minus L is the x n minus L into not xl, xn. This is Rxl for L negative. Okay, so L is less than 0, which means that if L is less than 0, one second, xl. Now Rxl is this, but for L negative. Now this is how Rxl is defined, but for L negative. So L negative means, now this L negative means that n must start from L. Otherwise, if like this, if you start n from 0, for L negative it will go to x minus L, which is not there. That value is not there. So you could have defined it from this to n minus 1. this you could have defined as RxL for L negative. You could have, right? But you are not defining that. Why? Because this is not equal to this. That is, then RxL and Rx of minus L will not be equal in general. So are you following? These two summations are actually different. What I am saying is that it's just a question of defining the summation over an appropriate set of indices such that each value is falls within 0 and n minus 1. Now for positive L, if you want to impose those, then you have to put these two limits. If you want to do it for negative L, then you have to do it for these two limits. Now the moment you change the limits, the value of the sum is going to be different, because XL, I mean, there is nothing to guarantee that these two sums are going to be different, going to be same for a given sequence. So which will immediately mean that RxL will not be equal to Rx minus L, and this is a very fundamental quantity. I mean, this is a very fundamental requirement of the autocorrelation matrix. So this will mean that the larger autocorrelation matrix will not be symmetric. All sorts of complications will arise. So therefore, we actually just deliberately define it like this. That is we only define the sum for positive L, and then we say that if L is less than 0, then it is equal to Rx of minus L. So it is always defined in terms of the positive L, so that the RxL and Rx of minus L are always forced to be, by definition they are same. Okay, and it is 0 elsewhere. So RxL is now defined only from minus n minus 1, that is L can take value from minus n minus 1 to plus n minus 1, simply because you have samples from up to minus n minus 1. So therefore you cannot define correlation beyond that. If you want to define correlation beyond that, it is going to be highly erroneous. Now actually if you want to define correlation beyond that, you will not get values, and even if L approaches close to n minus 1, just imagine that the total number of terms in the sum decreases with L, right? So finally when L becomes equal to n minus 1, you have only one term left. What does it mean? It means that you are using a product of one term of one realization to estimate an expectation of a stochastic process. So it is going to be highly unreliable. See, you must to make it reliable, you must base it on more data, and you must take an average over large number of data. So therefore in general, if you L should be much smaller compared to n, only then the estimate of this correlation is going to be reliable. Otherwise its variance will be too much. See the estimates are reliable only if L is much less than n. Otherwise it is going to have too much variance. So that estimate will not be reliable at all. And another important thing is that this estimate is actually biased for a given L and n. Why? Why is it biased? Because if you take an expectation of this sum, what is going to be? So if you take, see, this is the single realization correlation that you have calculated. Now let us take expectation of this. Question is, if I take expectation of this now over multiple realizations, does this converge to Rx, the true Rx? It doesn't. Why? Because if you put expectation here, all these terms will be expectation, right? So each one of them will actually become Rx. This is the true Rx once you have taken expectation. Now here you have how many terms? N minus L number of terms, and you are dividing by n. So you are actually having 1 minus, I will put mod L because L can be positive or negative, into Rx. This is expectation of Rx hat. Can you see this? So you see that for a given L and a given n, expectation of Rx hat is not Rx. So even if you take several n length signals and took an expectation of this over multiple signals, you will not get the true autocorrelation. So this estimate is biased for a given L and N, but obviously this term will tend to 0. This term will tend to 0 as n tends to infinity. So this estimate will become unbiased, that is, it will actually converge to the true correlation provided you have taken a large number of data points compared to L. Right? This is, I mean, intuitively quite. So this estimate is as such biased, but it is asymptotically unbiased. Asymptotically means as capital N tends to infinity, it will become unbiased, but as such it is biased. Okay? But still these estimates are used. For example, it is very easy to actually remove this bias. For example, if you had taken this estimate, that is, what is the idea? The idea is that here you have n minus L number of terms. So here, why are you dividing by n? Divide it by 1 by n minus L. That will make it an unbiased estimate. But there is a problem. The problem is that if you do that, then it can be shown that the overall Rx matrix will not remain positive, may not remain positive definite. Rx matrix is supposed to be a positive definite matrix. That is, X transpose Rx must be greater than 0 for all X. Remember that in our earlier class when we had talked about the normal equation, we had assumed that the R matrix is positive definite. Now if you use this formula, it turns out that this matrix may not remain positive definite. Therefore, people prefer to work with this definition of correlation, keeping in mind that n should be sufficiently large, because otherwise if R is not positive definite, it can lead to all sorts of anomalous results, like your power spectrum, that the power spectrum that you calculate based on this R may become negative, which is clearly an absurd result. The power spectrum cannot go to negative. So in the literature, mostly people will work with this definition, and so we have to only remember that this definition will lead to, it is a bias estimator, but the bias will go to 0 as n tends to infinity. So we should take a sufficiently large value of n. That is what we should remember. Second thing is that of course it is also, this estimator variance, these proofs are pretty difficult, because if you want to calculate the variance of this, see, this itself is a second order moment of the samples. If you want to calculate the variance of this, then you will in general require fourth order moments of the sample. So it is quite involved, but people have done it, and people have found that between these two, this has a better variance, lower variance. So that is also another positive point for it. Just to mention, we are not going through all those calculations. So now we come back. So now we have got a fairly intuitive formula for calculating autocorrelation. Simple time average between samples which are L apart. Right? Very simple formula actually. That's what anybody would do. Now let us see that how to calculate this the power spectral density from this. So we review some basic things. So here is here I am describing a very interesting result, which those of you who are reading DSP, I cannot really go into the proof and all that, but those of you who are doing DSP will probably study in much more detail. That is very interesting. That is, see, suppose we have a continuous spectrum. We have a continuous spectrum of signals. Some things, suppose we have some time domain signal. This is xt with respect to t. Suppose it has some spectrum. Generally spectrums are, this is x omega, Fourier transform of xt, this is omega. Now what will happen if you sample this and get a sampled sequence? and then after sampling, if we take its Fourier transform, what will happen? We know that x omega will now become periodic. So we will get a, if we sample in the time domain, this will become periodic in the frequency domain, right? This is obvious because it's a periodic function of omega. It will become a periodic function of omega. Now the question is that, so this is what? This is our Sxx omega. I mean, this is actually x omega, rather x star omega, where x is, this is, if this is x star t. Now the point is that we can even sample this one, that is, we can sample the frequency response itself and get the value of the frequency response at certain points. Now from these sampled values, I can, by what is known as an inverse DFT, I can go back to another, to a sample time sequence just by an inverse DFT process, and that sample time sequence will be a periodic version of this. So if you sample in one domain, you get a periodicity in the other domain. So if you sample in the time domain, you get a periodic thing in the frequency domain. Now if you sample this thing, you will get a periodic time function, periodic sample time function, because this was the original time function. So if you sample this, you will get this time function periodic, right? So this is an interesting thing, because sometimes what happens is that, I mean, we must know this interpretation, because in general we will be calculating these, that is, whenever we will calculate the inverse DFT, we should know that what we will get is actually a periodic function, and between that is within the fundamental period we will get the actual samples. At other times we will get same thing repeated, right? So that is what we are saying, that now here when we compute an n-point DFT, now we are computing an n-point DFT. That means we have got an n-point signal. Based on an n-point signal, we can calculate an infinite point DFT. If we take the DFT of that signal, we will actually get a continuous function x omega. Now that we can sample at various points. So then this is that. So x tilde k is xn. Now you see that this is not a general omega. This is sampled at some equidistant omega points, twice pi by capital N into k. So you are sampling the frequency response. Now based on this, you can get back an xn sequence through an inverse DFT process that is defined like this. These are this is the well known n-point DFT formula, and this is the well known n-point DFT formula. Now you see that this thing is actually periodic in n. Obviously, here k is varying as an index and n is here. So obviously, if rather than n, if you have, for example, for n is equal to capital N, twice n, thrice n, it has the same value. So therefore this is periodic in n. That is how you get a periodic function. This is just an interesting observation which we have to remember. Now what is our objective? Our objective is that we have to find out the power spectral density from a realization, that is, we got some samples from 0 to capital N, and we want to calculate what is Sxx omega from there, some estimate of it. Obviously we cannot calculate the actual one. So what are we going to do? So first we again define the same correlation function. I have used a different notation. Different parts are taken from different references, so sometimes the notation is, but this is nothing but my same old RxL that I had talked about. It is the same thing. Okay. Only thing is that I have not put this x index here, rather than I have put an n index just to indicate that there are n points. It is a finite length sequence thing. So this is the formula that we had seen previously, same formula, and what is limit of n tending to infinity r and m? Obviously it is rx x m, limit n tending to infinity, because why? See, I have not taken expectation, I have just taken n tending to infinity, because I have assumed that the process is ergodic. So if the process is ergodic, then time average is equal to ensemble average by assumption. So this time average, long time average will converge on the ensemble average. So therefore this will be equal to this. If I take an expectation of this, it will obviously match here, whether it is ergodic or not, but I have not taken expectation. Because why I have not taken expectation? Because taking expectation is of no use to me. I want to calculate based on one realization. So when can previously I took expectation just to show a property, but now I want to compute, so I cannot take an ensemble average. So I only want to stay in the time, only time averages I can use. Now if I define a Fourier transform of this, you see what is my objective? My objective is to calculate Sxx omega, which is the Fourier transform of this, but I can calculate only this. So I am defining something which is a Fourier transform of this, something which I can calculate, and then I will see that how good an estimate that is. Incidentally, this estimate is known as the periodogram. It is a very famous estimate. Historically this is called the periodogram. Okay. So we will see that how good this estimate is for the true Sxx omega of that process. So first of all, how do we calculate this? One way of calculating this is through this formula. See, given the sequence, I can calculate this. Once I can calculate this, I can calculate a Fourier transform, so I can calculate this. This is one way of doing it. There is another way of doing it. So that is based on this observation that 1 by n into magnitude of xn omega whole square is equal to in omega. That is, if you take the sequence, if you take its n point DFT, that is in general a complex quantity. If you take its magnitude square and then divide by 1 by n, you will get the same thing. So this is another way of, one way is to take the samples, first compute autocorrelation, then take Fourier transform, that is one way of doing it. The other way is right in the beginning, they get the sample, compute DFT, you get xn omega, then take its magnitude square, that will give you in omega. That is another way. Why? Because of this simple, I mean this is just sort of an identity that if you have in omega can be written like this. This is my r hat n m, just simply substituted, okay, and this is my xn omega. So if I multiply this xn omega magnitude square means xn omega into x star n omega, something multiplied by its complex conjugate will give you magnitude square. So this is xn omega and this is again xn omega for star. Only I have written two different indices. Here I have used k, here I have used l. Now it is nothing but an a plus b plus c into x plus y plus z type of thing. So you will get all ax, by, cz, ay, az kind of terms. So I have now those terms I have combined and I put it here. See, this is minus j omega k, so you are getting minus j omega k. This is minus j omega l star. See, this part is real, only this part is complex. So when you take star, this will become plus. Therefore minus minus plus, and only these xk xl terms have been combined. Very simple. So now compare this with this. See, here also you get xk xl kind of terms, and here what is m? M is the difference between this index and this index, and that is appearing here. So here also same thing, two different indices and the difference between these two indices appear here. So these sums are same. So therefore 1 by n xn omega square equal to I n omega. Just nothing, just substitute and rearrange terms. So now, so we have got these two ways of calculating the periodogram. Now, so we are saying that it is an estimate of the power spectral density. How good an estimate it is? So whenever we want to examine how good an estimate it is, we want to see its mean and its variance. So its mean is simple to estimate. Its mean is this, simply just take expectation here. So if you take, we already know that the expectation of this is this. Remember that we said that it is a biased estimate for a given n. So it means that this is also a biased estimate, but it is again asymptotically unbiased. That is, if n becomes too large, very large, then this will converge to Rxx, and then this will converge to Sxx. So again, it is an asymptotically unbiased estimate, the periodogram. But the problem is that its variance is very large. So this is the asymptotically unbiased estimate result. That is, if you compute this estimate, if you really do it for large n, then the expected value of that estimate is the true value. So that's at least a good thing. And we'll see that now expected value being large, I mean being true, gives us some reassurance, but then when we are doing for a single realization, it is not much useful unless the variance is small. And incidentally, the variance is very large for this estimate. So in the raw form, the periodogram estimate is a very poor estimator of Sxx omega. So it is asymptotically unbiased, but if you can again compute it in a very complex way under certain assumptions of Gaussianness, etc. But it turns out that the variance of this estimate is almost equal to its value. So if you want to estimate suppose some value x, and if its variance is of the order of x, then you are pretty uncertain, isn't it, about it. You are only certain about it if suppose you are trying to estimate something whose value is 10, and if your variance is say 0.1, then it may be acceptable. If your value is 10 and if your variance itself is 10, then you could be anywhere between around 20, 30 also. So you can be, I mean, pretty much off from the real value in a single case. That's why this estimate is very unreliable. So the raw periodogram estimate is not reliable at all, though it is asymptotically unbiased. Not only that, very important thing is that as n tends to infinity, this variance does not decrease. So just by taking a large number of samples, you will find that the mean will converge to the true value, but the variance will not decrease. So you can't do it like that. That's an even bad one. What's point? So therefore, it cannot be used just like this. There has to if you want to compute the periodogram estimate, you have to do further processing on it. And people see, if you have some randomness which is rather large, but if you have them as kind of uncorrelated, then one standard way of reducing variance is by doing an averaging. Now, so there are two kinds of averaging which are now proposed for periodogram estimates to reduce their variance, because otherwise variance is too large. So those two are, one is smoothing, another is averaging. So what they are, that is very simple. So the first approach says that suppose you got a periodogram estimate which is, first approach says that don't take, suppose you got a periodogram estimate which is like this, on this side also, they will be symmetric. So suppose you've got it like this, and what it says is that if you want to get an estimate, smooth it means take averages over little frequency intervals. So that is like low pass filtering. So if you do low pass filtering, what will happen is that this will track, it will become like this. So the variance will decrease. But what will happen is that your frequency resolution, now what you are doing is you are taking all samples of periodogram estimates over a frequency range delta omega and you are simply taking average, that is this formula. So you are first calculating the periodogram estimate over all samples, then you are taking small bands of frequencies and you are calculating an average, simply 1 by 2m plus 1 summed up from the same sequence. So what will happen is that now the smooth sequence at every time is actually a function of the old sequence for the last delta omega. So your frequency resolution is gone. You cannot catch the variations of frequencies over small frequencies because you are going to average them. So the curve will become smooth. So that is what you are sacrificing. So you are sacrificing on your frequency resolution to get an estimate which will not vary over experiments. So you are saying that okay, this may not be so accurate in frequency, but it is fairly close to what is going to happen even if I take 10,000 such experiments. So I am increasing my reliability at the cost of my frequency resolution. See, something you must do. Okay. So this is the what is known as the smoothing approach. And okay, finally we will see that how they are similar. What is the other approach? So here what you are doing is you are taking a data sequence, the whole periodogram you are computing. After you have computed it, from that periodogram you are doing averaging on the frequency axis. Rather than that, you can do what is known as a sort of a virtual ensemble averaging. That is, not do an actual ensemble average. See, you got a long sequence, so I will say that no, I will chop this sequence into smaller time sequences. So out of one long sequence, let me make 10 small sequences. So then corresponding to those 10, I can make 10 periodograms, and then I will, once I calculate 10 periodograms, 10 different periodograms, so I will simply average them. That is something I can do. So that is the other approach, which says that divide the data sequence into k subsequences, obtain periodogram of ith subsequence, and so you can calculate this, and then for a sequence xin, now these can be overlapped also. It's not that they have to be, I first time said that they are chopped. They could be chopped or they could be overlapping. That is, first sequence begins. You can also do it in an overlap manner. That is, if you don't have too much data, then if you have large number of data, then you can chop it. If you don't have too much data, then you can use these two, then you can use these two, then you can use these two. You can also do that. Okay. So intuitively quite simple, right? So you are somehow from the data you are trying to do some averaging. You are trying to create a situation so that you can do some averaging, expecting that the uncorrelated things which are coming from sample to sample, by averaging they will come down. Okay. So what you are doing is, so you can have in general you can define xin, that is a given sequence like this, and if d is less than L, then the segments will overlap, and if d is equal to L, then they will be one after the other, contiguous. And then you can, this is the overall averaged periodogram, which is simply the average of each one of the periodograms. So you sum them and divide by k, right? And it turns out that obviously the expected value will match with the original expected value, because it's a linear operation that you are doing. But the variance will now be 1 by k times. Now what is the comparison between these approaches? For example, there you were losing spectral resolution. Are you not losing spectral resolution here? Definitely you are losing, because of the fact that see that in the endpoint DFT, if you have an endpoint DFT, then what is your discrete frequency resolution? It is twice pi by n into k. These are your discrete frequencies at which you can get the DFT. So if you reduce n, then you are getting larger. So you are not getting the DFT at finely closed frequency points. If you do a 10-point DFT, the DFT will, the frequencies at which you will get the DFT, and if you do a 100-point DFT, you will get it at much lesser frequency resolution, much finer frequency resolution. So in the second approach also, see, the first approach you are losing resolution because you are averaging. In frequency you are averaging. So it is quite obvious that you are losing resolution. In the second approach you are not averaging in frequency. I mean, you are sample to sample, but since you have divided the data sequence into k segments now, so in each segment you now have less number of data points. So in each segment having less number of data points means in each of these periodograms frequency resolution is already gone, because you have less number of data points. So here also you are losing spectral resolution in a way. So I mean, it cannot be any different. Only thing is that these are two different ways of doing it. But finally, if with a given amount of data, if you want to have reliability, then you cannot have resolution. So there is a certain amount of information that you have finally, I mean, actually got. So you cannot it is not expected that by one method you can do something miraculous over another method. Generally, I mean, if both the methods are good enough, if you can do that, then one method is not so good. So this is what we are doing, and finally we come to we had known that we not only need these Rxx kind of quantities, we also need Rxy kind of quantities, and they are absolutely similar. So we need not elaborate that too much. You can so if you can calculate, so the exact ways that you have calculated Sxx, you can use exactly similar ways to calculate Sxy and R hat xy, given two sequences now, xn and yn, again over 0 to n minus 1, given two finite length single realizations of a stochastic process, exactly by similar formulae. For example, the correlation formula will now become this, okay, and see, here it is not forced like that, because Rxy need not be exactly symmetric, and these are so you can once you have this, and you can for example Sxy, see the two ways of calculating. So one way of calculating Sxy is directly calculate yn omega by dft, directly calculate xn omega by dft, and then multiply and then have this realization. That will give you Sxy omega. That is the direct way. Another way is compute Rxyl and then use this formula to calculate Sxy omega. That is also another way, just like the previous case. So you can either calculate through the autocorrelation, or you can calculate through the direct DFT of the signals. Both are possible. And actually, you know, these, if you see a DSP books, you will find that there are lots of, you know, window function. There is something called a window function in DSP, which is used to convert finite length sequences, I mean one sequence into another, and based on these properties of the window function, you get certain properties in the frequency domain. So there are very nice window function interpretations of many of these operations. So if you are interested, you can see that, but we don't have so much time to carry all that. So we'll stop here today. So what we have seen is, basically what we have seen is how to calculate autocorrelation and cross correlation, how to estimate the autocorrelation and cross correlation of a stochastic process from a finite length single realization of that. That is, I will get only one string. The stochastic process is an infinite number of strings. Depending on the outcome, you get one of them. But I have only one string as measurement, that too between only a finite number of samples. From that, how can I estimate the the properties, correlation and spectral density of the whole process. So we saw some estimators of that and found their properties, whether they're biased, unbiased, variances, etc. So I will stop here today.